The presentation today we're going to break up into a few parts. We have the background, which is giving you a little bit of background about NIST and what the Fire Research Division does. And then we want to talk about what is fire in the United States, what is the problem, and then get into the firefighter's workplace and how has that changed over the past few decades. Then we try to tie in these changes with fire dynamics and fire behavior, and this is usually good for the layperson because most people, I don't think, appreciate just how fast a fire could grow and spread in their home. And of course, earlier this week, there was a very tragic fire in New York City where 7 children lost their lives due to a rapidly spreading fire. How are fires in homes different today? We'll talk a little bit about that, and then get to the sort of the meat of the subject. How do we take our laboratory to the street? How do we take the fine measurements that are done at NIST and replicate them in acquired structures that are getting ready to be torn down? And you'll get a little insight into that. And then we'll close with the lessons learned and how we try to share this information with the fire service. So the Fire Research Division works on a wide range of issues. Basically, we're trying to focus on reducing the loss of life and the loss of property from unwanted fire. It's not exactly our official mission statement, but that's the gist of it. We do that by, we've developed smoke alarms, and we continue to work on developing new smoke alarms, doing demonstrations with automatic fire sprinklers to show how efficient and effective they are, emergency egress studies, reduced furniture flammability. There's been great progress made in the case of mattresses. If you buy a mattress today in the United States, it's a much more fire-safe mattress than it was in, say, 2005. So there's been great gains there. We're currently working on things like sofas and upholstered furniture and whatnot. Another way to look at the problem is if we can't make the furniture safer, do we try to reduce some of the ignition sources? And so NIST worked with the tobacco industry and others to develop standards for the reduced ignition propensity cigarette, sometimes inappropriately referred to as a fire-safe cigarette. It's just reduced ignition propensity. NIST is a world leader in developing fire models of all sorts. The one that's mostly in use currently, the state-of-the-art, is the Fire Dynamics Simulator and its partner program, SmokeView, which is how you view the results and visualize the results. These fire models are used in research, design, and litigation around the world. It's really the standard for fire models around the world. A new group that we have started is looking at issues regarding wildland-urban interface fires, as that's becoming more and more of a problem in a large part of the country that are suffering from droughts and dry weather, and building more and more suburban urban sprawl, so to speak, into the wildland. So it's really not the trees burning necessarily that are the bigger problem. It's when the trees catch the houses on fire that becomes a very major problem. And as you watch the news this summer, you'll see events of that. So we're trying to understand how to mitigate that hazard. And currently, a large portion of our team is working very hard to bring online a unique state-of-the-art National Fire Research Laboratory. It's an investment that was made a few years ago of over $27 million, and it will really provide some unique capabilities in terms of testing structures and structural capabilities against fire. The group that I lead is the Firefighting Technology Group, and our main objective is to help firefighters do their job better, and by doing that, also help them do it in a safer manner. Again, we want to reduce losses from fire, both in terms of life and property. In addition, we want to provide data and test methods so we can improve firefighters' protective equipment. And last but not least, the firefighters are the ones going out there every day to deal with our fire problem. And we need to get this information to them. We need to make it part of their training. We need to make it part of their education so that they have the best tools, techniques, and knowledge to deal with fire. NIST doesn't do this alone. We work with a number of other federal agencies, as you see the list here, ATF, Consumer Product Safety Commission, NIOSH. They have the federal mandate for investigating firefighter fatalities. We have a group at NIST that works with the law enforcement side of the house, National Institute of Justice and others, and we collaborate with them on a number of issues. The Nuclear Regulatory Commission is playing a major role in validating and verifying our fire models right now, so that's an important partner that we have. Department of Homeland Security and the U.S. Fire Administration, of course, that oversees a number of programs with regard to improving the fire safety in the United States. We also work with a large number of professional organizations, as you can see there, included in the list: the Association of Fire Chiefs, International Association of Firefighters, International Society of Fire Service Instructors, and many others. The partners I'm really thankful for are these fire departments that we have listed here, as well as the universities and the private laboratories. These are the folks that get together with us and actually get their hands dirty, actually run fires together, run experiments together. And so in the case of the fire departments, basically, they're willing to own the fire because the lawyers at NIST don't like us to go around the country lighting buildings on fire. So we need to have a partner fire department that has the capability to control the fire and put the fire out, and basically take a chance on us because they're investing resources, which are usually in high demand in their town, to continue this work to try to improve firefighter effectiveness and firefighter safety. So what is the fire problem in the United States? Well, according to NFPA, the National Fire Protection Association, in 2003, we had over 1 million fires reported. There were approximately 3,000 civilian deaths and almost 16,000 civilian injuries, and $11.5 billion in property damage. How has this changed over time? Well, this has been an exciting time to be a researcher, if you will, in fire, or to be a firefighter, or to be a codes official or a fire prevention officer, because you can see that some of your work has had quite an impact in reducing the number of structure fires in the United States. They've decreased by 57% since 1977. Coincidentally, I started at NIST in 1979, so this has been a pretty good track record. It's leveled off here toward the end, so we still have to keep at it and push on it. The other thing to note is that civilian fire deaths in the United States have also decreased by 56% since 1977. And again, a very important note. What you see on the yellow line on the bottom, however, are where people die in fire. And they typically don't die in fires at work. They don't typically die in fires when they're shopping. They don't typically die in fires when they're on vacation at a hotel or something. They typically die in the place where they should feel the safest, in their own home. That's where the majority of fire deaths have occurred over time and continue to occur. In fact, you can see it's becoming a larger percentage as time goes on of all fire deaths. So that's really a big focus for us in terms of improving fire safety in the home. Now, we've seen all these curves that are just on this nice reduction, so things are going along fine, but there's one curve that's not reducing at the same rate, and that's firefighter deaths on the fire ground. And as you can see, that curve is kind of bucking the trend, and it's a very disturbing trend. According to Dr. Fahey, again at NFPA, in the late 2000s, firefighters, due to traumatic injuries on the fire ground, are dying at a rate of 3 deaths per 100,000 fires. Where in the late 70s, when they had less protective equipment, potentially less training, the death rate was lower. So what's going on? Well, what do firefighters wear? In the mid-80s, by that point in time, pretty much all fire departments had adopted the use of the self-contained breathing apparatus, or the SCBA. So those are the tanks that you see on the firefighters' backs. You see they have protective helmets, they have protective face pieces, they have turnout gear, which are very heavy and specially designed pants, bunker pants, and a coat. They wear very heavy gloves to protect them from the heat, protect them from abrasions and things like that. So we're trying to protect them from a range of hazards in that structure. Unfortunately, and they also wear very big and heavy boots. Unfortunately, you might imagine that when you start to put on 30 pounds of gear and you start to carry tools which may add another 10 or 20 pounds to the load that you're carrying, it can affect your balance. It can affect your stability. It can affect how you crawl around and your ability to move around. Also, with the SCBA, may have some impact on limiting your vision as well. Well, why is this important? Well, if we look at the two photos on the bottom, and if you live in the Washington, D.C. area, you'll recognize that there were a lot of homes like this that were built in the 1950s and 1960s, just inside the Beltway and just outside the Beltway. You also see some row homes up there, very common inside Washington, D.C., very common in Baltimore. And then we have sort of the little mansion up there in the left-hand corner. So these smaller homes are about 1,200 square feet or so. The larger home in the picture there is in excess of 4,000 square feet. That makes a difference in the size fire that the firefighters may have to deal with when they arrive. Other things that you can notice just looking at the outside of the home is the pitch of the roof. Firefighters typically want to get on the roof and make a vent to let hot smoke and gases out. Well, when you have a relatively small flat roof, like the single story, that's not too hazardous an operation. When you have a high-pitched roof that's now 30 feet above the ground, that becomes more of an interesting opportunity for the firefighters. The windows are different. The amount of windows are different. So when they vent, they let in more oxygen that can mix with the fire gases that are already inside the house. Something you can't see from these pictures, but we know from experience, the older homes had more compartmentation to help limit fire spread. The large rooms in the older homes might have been 12 by 20 feet. The bedrooms were typically, a big bedroom was 12 by 12. In the more modern homes that use engineered lumber to increase the span, we can now have two-story high openings inside that home. It could be 40 feet long, 30 feet long, 30 feet wide. Very large openings with no compartmentation, nothing to stop the spread of smoke. And as we look at the back of the homes as well, we see additional windows. We also see there's combustible decks on the rear of these large homes. We're starting to see a trend across the United States where mini fires are starting outside on the combustible deck in the wintertime due to mishandling of ashes from a fireplace, in the summertime from grilling or using a fire pit of some sort on a wood deck. The fire gets into the siding of the house, it runs up the side of the house, gets in the attic. By the time the firefighters get there, if they don't perform a full size up, they don't appreciate where the fire is and can get caught by surprise. And unfortunately, a fire like this killed a firefighter in Prince William County not long ago, Kyle Wilson. And in Loudoun County, there were several firefighters that had to literally jump out of windows to save their lives. What do we wrap our houses in today? Plastic. We have plastic, we have a lot of insulation in our homes, and this is a good thing because we want to save energy. We want them to be energy efficient. The challenge is if a fire starts in our home now, all the smoke and heat is going to get stored inside the home and basically waiting for the firefighters to arrive and make entry. Our thermal pane windows are more resistant to failure in terms of heat because glass is such a great insulator. And so the interior pane will absorb most of the energy and slow down the potential for failure of that glass. So if the oxygen runs out inside the structure before the glass breaks, again, it's going to change what the firefighters find on the fire ground. When we see these homes burn and we see all that heavy black soot in the images, that means that it's a fuel-rich fire. That means that the fire has not mixed with enough oxygen fast enough in order to have a clean burn. In fire department vernacular, the condo project that's there in the upper right-hand corner would be considered fully vented. The windows are all out, the roof is off, and yet it's still a fuel-rich fire. In the 90s, we worked with the Phoenix Fire Department to look at structural collapse issues. So here's a traditional construction, older construction, heavy timber hardware store that they're getting ready to tear down. So they let us burn in it. You notice that we had flames, and then we didn't have flames. We just have smoke until we sent a firefighter to the front door to open up and let more air inside the structure. Once the firefighter opens up the structure, we get a reemergence of flames at the roof line. And within 10 minutes of them opening the front door, we're going to have a fairly significant structural collapse. That if any firefighters were in there at that time, clearly they'd be injured or killed. So these things happen pretty fast in the big scheme of things. By the time that somebody notices the fire, somebody calls in the fire department responds, the clock is ticking, and the physics of the fire keep going. It's not watching the clock. Because the fact of the matter is, wood, which is a very sustainable fuel, burns. And the worst place to have wood is up high in a space, because when a fire burns, the hot gases go up to that space and start to pyrolyze the wood. There have been great gains in property protection and protection for occupants in some of these large wood structures that are being built all over the country in the form of condominiums or mixed-use structures with businesses on the first couple levels and then wood frame structure above them for residential. The challenge is they don't sprinkler the entire building. So all that attic area that you see in the upper right-hand corner there would have no sprinklers in it. It would be a mechanical space. And we just had an example of what happens of that about a month ago in New Jersey when they burned down a large condominium complex. Once the fire got up in the attic, there's no way the firefighters can stop it. And firefighters are getting additional challenges every day. More people are putting solar panels on their roof. They're getting fuel cells in their home. We have all sorts of different power sources for vehicles nowadays, hybrid vehicles, batteries, compressed gas. I understand the hydrogen car is coming, so we'll see. And that can be very exciting as well from a fire perspective. So in summary, to look at some of the data from our brothers in the Census Bureau, houses in the United States have gotten quite a bit larger on average from the 70s to the 2000s. The housing lots are getting smaller, so these bigger houses are getting closer together. Again, bad news for fire development. During the past 50 years, the fuel loads in our homes have changed dramatically. They've gone from being where our furniture was principally made of cotton and steel springs, and you needed the steel springs in the cushions because the cotton would kind of bat down. Cotton will smolder. It's fairly easy to ignite, but it burns slowly. Polyurethane foam, which has replaced cotton as the principal foam plastic in our furniture, is extremely resilient. It makes a great seating material. It's hypoallergenic in a sense. So I mean, it's a good material until it catches fire. And then when it catches fire, it has a much higher heat of combustion than the natural materials. It burns with a high amount of soot, so it's a very dirty fire, and it results in fuel-rich conditions within the home very, very quickly. This kind of burning, in simple terms, we say it burns hotter and faster. So what that means is for occupants, you have much less safe time to get out after you hear your smoke alarm. And of course, if you don't have a smoke alarm, you're doomed. As we mentioned, the home designs as well have changed. So fire dynamics, what is it? It's a relatively new science. The first textbook on fire dynamics wasn't written until 1985. People have been studying fire for a long time, but typically in very separate disciplines, looking only at the chemistry of the fire or the heat transfer, the heat release rate of the fire. And then they started to bring it all together, the material science, the fluid mechanics, to see really what it takes for a fire to interact, to ignite, to spread, and develop. So what is a fire? In basic terms, it's a gas phase exothermic chemical reaction. In other words, it emits heat and light. So the fire tetrahedron is composed of, we need a fuel, we need some sort of oxidizing agent. We have 21% oxygen in the air we breathe, so that's our oxidizing agent typically. We need some heat, our ignition source, and then for it to have these flames, we have this uninhibited chemical reaction. But the key thing is the fuel needs to be in gaseous form. Solids don't burn and liquids don't burn. The oxygen is in gaseous form and the fuel needs to be in a gaseous form to mix with it and the heat in order to have a flame. So let's take a look at that. Let's take a look at our fire tetrahedron. The heat source will heat up the fuel. The fuel will pyrolyze, basically give off a fuel gas. It will mix with the gaseous oxygen, and then a flame will develop when all the conditions and the concentrations are right. And then we have this chemical chain reaction that sustains the flame and keeps it going. And there we can see how that sort of evolves in a very artistic sense. Smoke is a fuel. So a very simple demonstration you can do to prove that is take a candle in a safe area and blow it out. And then bring a lighted match to the fire gases that are coming off the candle and watch what happens. The fuel gases ignite and the flame travels back down to the source of the fuel, which is the wick. So smoke is the fuel. That's the fuel that the firefighters need to manage more than anything. Fuels are very different today. If you take a piece of wood and ignite it with a candle, you see that it burns fairly clean and that the flame spread on the wood will be slow relative to, say, a piece of expanded polystyrene where you can see it's a very sooty flame, a very dirty flame, and the flame spread will be very quick. The pictures aren't that dissimilar from looking at this acetylene torch. In the fuel-rich case, the acetylene torch is not being mixed with, pre-mixed with oxygen. It's just a diffusion flame that's picking up the oxygen in the air. And as we can see, we have a weak flame and a very sooty flame. There's a lot of unburned fuel in those soot particles. When we add additional oxygen, we see we get a lot more energy out of the flame, and it burns very clean. So one finding that was developed at NIST in the early 80s was this idea of how much oxygen it takes to generate a certain amount of heat, that it became a constant. It didn't matter if we were burning acetylene or gasoline or cardboard. On average, for every kilogram of oxygen that's consumed, you generate 13 megajoules of heat. So basically, no oxygen, no heat. Fuels are different today. So under the legacy fuel, you'll see that we have a sofa that's, again, has some cotton batting and older materials in it. And we light it on fire, and we see that the fire doesn't grow very rapidly. With the modern furniture that's made of polyurethane foam and polyester batting, you can see that the fire growth is much more rapid, and the amount of smoke that's being produced is much more intense. Imagine that spreading through your home. So fuels are definitely different today. Pyrolysis. We mentioned this earlier. It's the chemical decomposition of a compound into one or more substances, basically just due to heat alone. Heat breaks down the material. So here's a look at a common sofa that you might have one very similar in your home. The seating cushions, the yellow material is the polyurethane foam. It's about 5 to 6 inches thick. The polyester batting is wrapped around it, and then the textile material that's covering it, in this case, is also made out of polyester. The back cushions you see are also just pure polyester batting, so they're a lighter weight, lower density material than the seat cushions. So watch what happens. We burn the sofa in our laboratory in Gaithersburg, Maryland, when we put an open flame to one of these sofas. Immediately you see heavy black smoke coming off. Again, an indication that it's excess fuel. In this case, that smoke is going into our calorimeter so we can measure the heat release rate. But in your house, that smoke would be collecting under the ceiling and starting to spread from one room to another. As the foam plastics start to burn and melt, they begin to drip and spread fire down to the floor level. This has the impact of now exposing that 6-inch cushion of polyurethane foam from both the top and the bottom to the flame as we see the flame start to pick up under the sofa. That increases the heat release rate and basically increases the hazard from this sofa. As the sofa starts to melt away, it allows more air to come in and mix with the fuel, and you'll see that the fuel is melting at such a high rate that you'll actually see it flowing across the board that we're using there to protect our load cell. So flowing fire. If this happened in a highway at a larger scale, they would call it a hazmat. The reality is, if you have a fire in your home today, it's a hazmat scene. So that sofa by itself, which only weighs a little more than 100 pounds, has more than twice the energy needed to flash over a typical scale residential room with an open door. You need about 2 megawatts to generate that flashover. This sofa alone has more than 4 megawatts. How many people only have a single piece of furniture and no carpeting in their home? So we started to get into compartment fires. And we understand that fire growth is a function of fuel property, quantity, ventilation, but all these things, compartment geometry, location of the fire in the room, and is there any wind? So in a very simple case, again in our lab, we're going to put the friend of the blue sofa, very similar blue sofa, into a small room with an open doorway, and we're going to light it on fire. If you remember from the previous video, it took about 5.5 to 6 minutes to get that entire sofa involved in flame. Here you're going to see what we refer to as a compartmentation effect. Because the smoke is being held over the sofa and the smoke has heat, it starts to radiate down on the sofa, preheating the sofa for the flame to spread faster. So we'll get more of the sofa involved faster. We'll eventually get enough excess fuel trapped in the room that the gases themselves will ignite remote from the sofa and start to spread through the room and transition into a phenomenon we call flashover. Notice that this is taking place in a little more than 3 minutes. So what is flashover? Flashover is the transition phase where we change from having a hot gas layer in the top of the room and a cool, fresh air layer in the bottom of the room to once that hot gas layer auto-ignites, the radiation from it auto-ignites almost everything else in the space. We have a well-mixed reactor basically burning from floor to ceiling in excess of 600 centigrade or 1100 degrees F. So let's look at another flashover. Again, I'm using my friend the blue sofas. And this time we have a dry Christmas tree. So that's a natural fuel, right? There's no synthetics in the dry Christmas tree. And what you'll see is that even that fuel will generate a fuel-rich condition. Heavy black smoke will start to come out of the tree. It's not mixing well enough to get it burned. And you'll see the fire triangle right in front of your eyes as the flames burn at the interface of the hot fuel gases and where it's mixing with oxygen as those hot gases are moving across the room. Now we're going to see a very clear example of pyrolysis. The radiant energy from the flames are now heating the sofa and the chair to such a point that the polyester is turning into a white fuel vapor, and that's going up into the hot gas layer, again, which will mix and burn at a later time once the concentration is right and once we have enough oxygen. Again, look at the speed with which this is developing. We had a tragic case in Annapolis, again last month, where 2 grandparents and their grandchildren were killed. They had a huge tree in a very large home, a 15-foot tree. NIST burned some 15-foot trees for the wildland-urban interface study. A dry tree like that can generate 30 megawatts of energy, or the equivalent of about 6 sofas going from 0 to maximum in a matter of seconds. Here's the most common cause of fires in the United States: unattended cooking. That's the #1 leader in the number of fires. And they don't look so bad initially. Someone walks away for a little while, maybe to go check on the kids, watch television. Some people actually have run out to the store to get an ingredient and left food on the stove. As you see in this 13-inch cast iron skillet, I've got a little bit of cooking oil. It auto-ignites due to the high temperature. And then the flame grows as energy re-radiates back into the pan. It extends our combustion zone. We start to see the flames impinging on the cabinets, which are made out of a engineered wood product, and they start to pyrolyze. And what looks like we're in almost an empty room, a 12 by 12 room with no other furniture than what you see there, you say, that can't go to flashover, can it? Well, let's take a look. The flames continue to spread. The off-gassing from the cabinets are now adding to the combustion, which is allowing the flames to impinge on the ceiling. We're re-radiating so much energy back into the pan that the oil that's left in the pan is starting to do what we refer to as boil over. It's bubbling and foaming and now spilling onto the surface of the kitchen range. Our high-pressure plastic laminate on our countertops is now bubbling and popping and pyrolyzing. And now you see that we're starting to get some ghosting flames or intermittent flames in the hot gas layer as it starts to move toward the open vent, the door. So now we'll take a look at the door and watch the vinyl flooring pyrolyze, auto-ignite, and quickly we transition to flashover. So how do the firefighters interact with this? Well, again, we discussed that they have some very good protective equipment, but their face piece is made of a plastic. It's an industrial plastic. It's a high-temperature plastic, but it's still plastic, and it melts at a relatively low temperature relative to the heat generated by the fire. Flame temperatures can be anywhere from 1,400 degrees to 2,000 degrees. And once that face piece reaches 280 degrees or 300 degrees, it starts to soften. And then it will be liquid pretty much by the time it's 400 degrees or so. Other equipment that firefighters carry into the space for their own safety, such as radios. There's currently no standard for firefighter radios in terms of how much heat they're required to take. So many of the devices that they carry in with them currently could melt at 140 degrees or certainly less than 200 degrees and fail them, where their gear is designed to take more energy than that. So we're testing all these things trying to work with the appropriate standards development organizations and improve the products and improve the materials that the fire service has. But in the meantime, we want to make sure that the fire service at least knows what the limitations of this gear is. Unfortunately, we're reactive in this sense in many ways. NIOSH has a program where they study firefighter fatalities. And the whole purpose of them studying these fatalities is to develop root causes. And they start looking at a trend here where there were a number of fatalities where firefighters' face pieces had melted, that was the first item to fail, that they still had air in their bottle, but yet they died inside the fire room or inside the fire structure. So NIST took that information and started to run some experiments to try to get an understanding of how this phenomena works. What is the face piece very susceptible to? So here we're going to light a fire with a very small burner. It's about 16 inches on a side. It's only about that big. We're going to fuel it with natural gas. It's going to generate a flame that as it moves up and down, as it pulses, it's about 3 to 5 feet tall. And it's about 6 feet in front of the mannequins. Now the mannequins are very specialized. They actually breathe. They have a controlled breathing device in them. So they're breathing about 40 liters a minute of air. And right now we have a camera inside the breathing mannequin's head looking out through the face piece. And so what you'll notice as you look through the face piece at the flame is that you'll start to see some crazing and damage occur to the face piece very early on. And we'll start to see the spidering coming out now. And then if you watch closely, this is sped up 10 times right now in the interest of time. We'll slow it down to real time shortly. You'll notice that the face piece is pulsing in and out with every breath the mannequin takes. That's how soft it is. What's a little difficult to see right now is that there is a hole in that face piece. And when we shut the flame down, it'll be very clear to see the hole in the face piece. So firefighters that have experienced this in, say, a training environment have told me that, they were warm, they didn't feel too bad, they certainly didn't feel a lot of heat on their face, and then all of a sudden it felt like, just a blistering, a burning on their forehead or on their cheek, wherever that hole had opened up in the face piece. And there you see how soft the face piece is as the hole is pulsing and moving with every breath the mannequin takes. So radiation is really one of the bigger challenges for the plastic face piece, and the reason is plastic is an excellent insulator, and it absorbs thermal radiation so that you could be in 200-degree air, but if you have line of sight with a hot fire, your face piece could get to 400 degrees or higher very quickly because it's absorbing that radiation. So if we look at comparison of some of the current standards for turnout gear, for personal alarm safety systems, the PASS device, for thermal imagers, things like that, we can see that they're all tested to at least 500 degrees. Everything except the SCBA, the self-contained breathing apparatus. And of course the reason is the plastic face piece cannot take 500 degrees. So the new standard that came out in 2013 based on work done at NIST now exposes it to a radiative heat flux of 15 kilowatts per meter squared for about 5 minutes. And the idea there is that it still may soften and develop a hole, but the breathing mannequin has to maintain a positive pressure seal for 24 minutes afterwards to provide time for someone to rescue the firefighter. So again, it needs to be combined with firefighter training so they know not to touch the face piece because it's so soft they need to leave it in place. And just to give you some references, we're talking about all these temperatures and heat fluxes and whatnot. The human skin at about 130 degrees has the potential to receive a second-degree burn injury. In other words, start to blister. Pain to exposed skin occurs at about 5 kilowatts per meter squared. That would happen within seconds. And the threshold for rollovers, we're starting to do that transition of flashovers, about 20 kilowatts per meter squared. When we actually have flames impinging on things, it's anywhere from, say, 160 to 200 kilowatts per meter squared. So firefighters are a traditional bunch. They're good folks, and every community in America is fortunate to have a fire department that they can rely on when they're in trouble, almost any kind of trouble. And fire departments nowadays are pretty much all hazard, whether it's auto accident, hazmat, responding to a terrorist incident. It's not just all about fire anymore. But they still need to be prepared for the fire when it occurs. And in the 90s, there was a big change in tactics, and that change was driven by technology. That change was driven by the adoption of the self-contained breathing apparatus, the development and acceptance of this bunker gear that firefighters wear. And they came up with some practices that whenever possible, they're going to attack from the unburn side to the burn side. And that kind of got reinterpreted to, we're going to go in the front door every time. Ventilation. It's defined as being a systematic removal and replacement of heated air and smoke and toxic gases from a structure with cooler air. However, that kind of got shortened and redefined to venting equals cooling. I'll show you that's not the case. When you vent a fuel-rich environment, a hot fuel-rich environment, and give it more oxygen, the fire is going to get bigger. The most aggressive and efficient fire attack is from the interior. Again, that turned into aggressive interior attack. And there's all this discussion about don't flow water from the outside. You'll push fire, you'll hurt people. Basement fire attacks always need to be done from the interior because, again, we're not going to flow water from the outside. And, of course, in some circles, when they just don't want to talk about it, they say, well, this is how we've always done it. So one of the first firefighter fatality incidents that I became involved with occurred in Vandalia Avenue in New York City. 3 FDNY firefighters died December 1998. And to look at the building, the fire occurred on the 10th floor. It's difficult to determine whether the fire apartment was on the downwind side or the upwind side, or whether there were 2 fire apartments based on the soot stains on the building. As it turned out, the fire was on the upwind side. And unfortunately, the door to the fire apartment was left open by the occupant. In the open apartment on the lower left-hand corner, a gentleman there was getting smoke in his apartment, and so he opened his windows to try to let some of the smoke out. Unfortunately, because he was on the low-pressure side, the downwind side, the intensity of the smoke coming in his apartment increased. Then he opened the door to his apartment and could not get out due to the high amount of smoke. So he went back in his bedroom, closed the door, and safely rode out the fire. Lieutenant Cavalieri, Firefighter Bohan, and Firefighter Bopp went through the smoke door from the elevator lobby. They were approaching the fire apartment and basically got caught between the fire apartment and the open apartment. They were in what we call the flow path. Once the windows in the fire apartment failed and a wind-driven fire occurred, a very high-intensity fire in that apartment, basically the heat dropped them where they stood and they died. This is an image of the corridor going from the fire apartment looking to the attack stair where the rescuers were coming, trying to respond to their mayday. This is what was left of the fire apartment itself. You can see it was hot enough to spall the concrete beams that composed the ceiling. And so the fire dynamic simulator, which wasn't even called that at this time, it was very rough and in draft stage. The fire dynamic simulator wasn't officially released till 2001. Was used to get a sense of what might have occurred in this fire. So you can see the little flicks of orange as the fire's developing in the fire apartment. And then we have smoke that's going to start as the fire increases in intensity. The smoke's going to pour out through the open door into the corridor. We see it flowing into the open apartment. And then we're going to see what the impact of the window failing, and we'll see a surge of smoke and flame pushing down the corridor. As the firefighters radioed their mayday, the other firefighters in the attack stair opened that door, and then you'll see that once they opened that door and it vented through that yellow vent on the top, the bulkhead vent of the stair, that flame also came in and burned them and slowed down their ability to get to the original victims. It took about 10 years to get the funding together, to get the partnerships together, and to really take a look at this by burning actual experiments instead of just looking at the fire model. And so in our laboratory at NIST, we built an apartment where we had a bedroom, a hallway. The bedroom's in the orange there. The hallway connects to the living room toward the bottom of the image. They're both 12 feet by 16 feet. The hallway's 12 feet wide. They open out into a corridor that goes 24 feet in each direction. In one direction it's closed, in the other direction it has an open vent, simulating a door to an open stairwell. There's a hollow core door that's installed in the target room that's in between the bedroom and the living room. So we call that our target room. Somebody could be safe there for a while, and we'll take a look at that. The flow path is basically composed of the volume or the rooms in the hallway, and then what direction the flow goes and where it goes is controlled by the inlets and pressure. So in this case, the high pressure area is going to be in the bedroom, and flow always goes from high pressure to low pressure, and the lower pressure is going to be the path through the living room and out the vent. It's pretty clear just by the colors I drew in the flow path that the higher hazard area for firefighters to be operating in is toward the outlet side, on the exhaust side, between where the fire is and where the fire wants to go. So we prepare these rooms just as you'd find in anybody's home with real fuel, real synthetic fuels. We measure the heat release rates of them so we have an idea of what the hazard is. So you get some idea at the peak heat release rate that a small upholstered chair is almost 2 megawatts and the sofa is about 2.5 megawatts. It's sort of a love seat size sofa. And the bed, king size bed there is 4 megawatts. We start the fires with the little waste container, and that's about 30 kilowatts. And the first test we did is a baseline test, and it has absolutely no wind supplied to it at all. So all the movement that you're going to see is a function of the fire acting as a pump, entraining fresh air in, heating the gases up, causing them to expand, increasing the pressure in the fire room, and then pushing out to lower pressure areas through vents. So the fire started next to the bed. On the upper left-hand side, you'll see the view of the window that's still intact. Once we break that window, or once that window fails due to the fire, you'll see a dramatic change throughout the space. Currently, smoke is now spreading through the hallway. It's into the living room that we see on the left-hand side lower frame. And we see in the thermal imager view on the upper right-hand side the amount of heat that's now pouring out into the corridor and moving toward the vent. If firefighters were in there currently and they were crawling, they would be safe. Their gear could protect them from that thermal load. But once the window gets vented, everything changes. And it changes within seconds. So now we have a situation that if firefighters were in the corridor, they would be exposed to untenable conditions. Within 30 seconds or less, they would have to either change that environment or find a different place to be if they hope to survive. Notice that at this point in time, the target room is still clear while all the other rooms are full of black smoke. The door to the target room starts to fail at about 6 minutes. So what's the impact on the heat release rate, the amount of energy that the fire is producing? Well, once we vent the window, it goes from 2 megawatts to more than 12 megawatts. The bedroom temperatures you see range from about 1,200 degrees Fahrenheit near the ceiling to about 500 degrees Fahrenheit near the floor. That all happens in less than 4 minutes, clearly untenable for an unprotected civilian. Once the window's vented, notice how we transition to flashover where we have well-mixed burning. Floor to ceiling, the temperatures all increase and they're all over 1,100 degrees Fahrenheit. What about in the living room? So let's say a firefighter was working pretty fast. They wanted to see if they could effect a rescue. They're working their way back to the fire room in that apartment. They're in the living room, and then that window fails. It goes from a condition that where they would be crawling would be 300 degrees or less to a condition where at a minimum it would be at least 750 degrees. As you might note from the chart I showed you earlier, none of their equipment can be tested to 700 degrees, can't survive 700 degrees. Your skin starts to blister and boil at 130 degrees. So again, an untenable situation. The velocity in the hallway. How fast heat is transferred to people is also not only a function of the temperature and the energy, but also a function of the velocity, how that hot gas is mixed and moving around your body or around the target. So initially, without the window vented, we just have a ceiling jet, or the gases near the ceiling are moving at about 6 miles an hour, the red line with the squares. As we get to the green line and the blue line, the green line is at 4 feet above the floor, and the blue line's 1 foot above the floor. Notice that once the window's vented, that high pressure pushing to the low pressure is now pushing a velocity, even at the floor level, of about 6 to 9 miles an hour. Anyone that's bought an electric oven lately, if you go in to buy an electric oven, they're going to sell you what type of oven? A convection oven. The only difference between the old school oven with the heating element and the convection oven is convection oven has a fan to increase the velocity of the hot gas moving around the turkey. What's the purpose of that? To cook the turkey faster. Unfortunately, High velocity hot gases take away the firefighter's safe time much faster. What about total unburned hydrocarbons? This is such a fuel-rich environment in the living room. We've got more than 12% of gases such as acetylene and methane that have been broken down from the materials pyrolyzing and getting ready to burn. That if we give it more air, that's the fuel that's ready to burn. Here's a case where we actually impose a wind on it. So again, you're looking at the inlet, which is where the glass is, and you're looking at the exit into the public corridor, which is where the open door from the apartment is. Once the glass fails, it's exposed to a 20-mile-an-hour wind pushing through that apartment. This is playing in real time, and again, watch how rapidly conditions for firefighters would change. Again, going from tenable for firefighters crawling in that corridor to untenable within seconds. How do you control it? Well, you don't want to give it an inlet or outlet. You have to control the flow path. One way of doing it is keeping the door closed. So in this case, even though the window's vented, the door to the corridor is closed. You can sort of see a steel rod in the image that we welded to the door in order so that we could open it safely without having to put firefighters inside that potentially lethal environment. So again, things for firefighters to look for. What's the wind outside? Can you see with the thermal imager smoke pushing with high amount of energy around the door? Can you feel energy coming around the door? In which case, don't line up in front of that door and open it, back out. Because if you line your crew up to make the push, that's what they're going to be assaulted with. Last one of the lab experiments. And this one's a good one because it actually happened to us, the phenomena that we're looking at here happened to us in experiment 3. It wasn't exactly part of the plan. It was just sort of something that occurred. And what had happened was that we generated so much excess fuel that it resided in our 40-foot by 30-foot hood with a 6-foot ventilation duct pulling 90,000 SCFM. Enough smoke sat there that it auto-ignited. And now that exposed the top of our test prop in the lab to a lot of radiation. We said, well, that was pretty interesting. Let's see if we can do that again and be ready for it so we can get a good video of it, get some good pictures. And also we want to see what the impact of putting a hose line through the window would be on this flaming that's going all the way from one end of the apartment, through the apartment, and up into our hood. So now as we watch the stack video view, which is sort of in the middle there on the bottom, we're going to start to see flames coming out of that. And they're going to pulse up and down for a while. Now we've auto-ignited the gases that are in our hood, our 30 by 40-foot hood, and now we're going to flow about 80 gallons per minute of water, a low amount of water in firefighting terms, into the bedroom. And you notice what happened. The fire went away in the stack immediately. And you might look and say, well, wait a minute. We still have flames in the bedroom. But as we're going to get our view back in the bedroom camera there, the second one from the left on top, we're going to see that we just have a bunch of debris fires basically going in there. What's left of the bed, what's left of some chairs and dressers and things like that. These are fires that firefighters' turnout gear are easily designed to withstand the energy and the heat from those and go in and fight that fire. The key thing is the water from the outside took away the fire gases. Firefighters' gear is not designed, and firefighters can't outrun when the fire gases auto-ignite and spread through the entire property. So within a month, we found ourselves out in the field in high-rises in Chicago and New York City, looking at wind-driven fires. And the fire departments had come up with a number of strategies that they thought would work to handle these kind of fires, but they didn't have any way of testing it. They didn't have any way of measuring how good it would be. So NIST went and instrumented these high-rise buildings with miles and miles of thermocouple wire and cable and videos to show this is what's referred to as a wind control device. By blocking the wind, you smother the fire, you cut off the pressure from the air, and you see that the fire in the living room was reduced significantly. The temperatures in the hallway dropped by more than 50% within a minute without flowing any water yet at all. Another idea is the floor below nozzle, or the high-rise nozzle. It's fairly lightweight, easy to maneuver. What you see in the inset there is that we have flames rolling the floor of the public hallway. Clearly, firefighters could not safely make entry into that public hallway. So what we're going to do is apply water to the bedroom of this apartment. So fire's going all the way through the bedroom, down the hall, through the living room, and out into the public hallway. And look at the impact that, again, flowing water from the floor below has on that fire. They make an adjustment to get some water in the window. There we go. And within seconds, the fire in the public hallway is out. Conditions are cooled down. The threat of a flashover or another flashover is gone. Firefighters can now make entry as they normally would on the fire floor, do their search, finish putting out the fire, and effect any rescues for any viable victims. We see things that we try to help the officers say, here's when you need to know when to size up. So we had natural wind this day. The wind is blowing the flames back into the room. At some point in time, the pressure inside the room gets so large that it basically shoots out a fireball. So, if you're a firefighter and you roll up on a scene and shooting out fireballs, start thinking about what plan B is. You shouldn't be marching down that corridor. It was commonly thought that if the window's vented and flames are coming out the window, then it's safer to be in the hallway. That's not the case. The homes are so fuel rich. We have so much energy stored in our houses that when it burns, like in this apartment here, there's a tremendous amount of flaming and burning energy going down the hallway. And this doesn't just happen in high rises. This happens in single family homes as well. In this case, 2 firefighters in Houston died. We were asked to come down to look at the fire behavior and model it. The victims went in the front door, which was the downwind side, the low pressure side. They made it to the back of the house. That's where their nozzle was found. And then their bodies were found in the front of the house, as you can see in the living room and the dining room. The fire started in the attic. It was well involved before the fire department arrived. They had at least 20-mile-an-hour winds coming from the rear of the structure, and you can see that's where most of the burn damage is. Where the people are standing down there in the image, that's where the front door is, where the firefighters made entry. The occupants had also opened the garage door because they were rescuing their cars. We made, again, a fire dynamic simulator model. What we put into the model is not only the geometry and the thermal and chemical properties of the fuels that are there, but also the timeline of what the firefighters' actions were. So you can see where we have little blue marks where ladder 26 made roof vents. We have another blue vent mark there just behind the front door where engine 36 was pulling the ceiling and things like that. The big feature that happened here were the windows on the back side of the house failed. When there was no wind, you can see that the blue, the cooler color, when we look at a cross-section of the house, was lifted, so the firefighters have refuge closer to the floor. Once the wind penetrated the house, it mixed the fire got hotter, and dropped the heat all to the floor. Just looking at it from the top down at the front floor view, 10 seconds before the glass failed, it was relatively safe for firefighters to crawl in there and make an attack. Within 10 seconds after the glass failed, it was untenable thermal conditions blowing out the front door. So as a fire officer, if you're ignoring the wind and you send a crew in on the downwind side, effectively you're taking a chance, you're flipping the coin as to whether they live or die based on whether a piece of glass less than 1/4 of an inch breaks or not. And again, here's another image showing the flow path where the intense heat is and how the firefighters got to a cooler place, but not cool enough for them to survive. So this brings us to a difference in what they had been taught. Firefighters for decades have been taught about the fuel-controlled fire, ignition, growth, fully developed, and then decay. So if we had a pile of pallets in a parking lot and we lit them on fire, or we had a campfire that we would light on fire, it's going to behave in this manner. As the logs go away, the fuel goes away, the fire's going to decay. When we put a fire inside a structure, we can create a very different kind of phenomena, the ventilation-controlled fire. And in this case, what we're showing is that the fire can't get to flashover, can't get fully developed yet because it runs out of oxygen. And then the heat release rate comes down, the temperatures come down until there's a change in ventilation. If there's no change in ventilation, the fire might smother itself and put itself out. If more oxygen is introduced to these hot fire gases that are stored in our well-insulated homes, the fire can reach fully developed stage in as little as 30 seconds to 80 seconds, 200 seconds, depending on the size of the box, the size of the house. So this has happened to firefighters many times. So let's look at an example. Again, working with the Chicago Fire Department, we had the luxury of burning 20 identical townhouses. I'm only going to show you one, but you know. See, we will have a beer, we can go through all 20. It's a good thing. You can see the living room on the front of the house, the dining room and kitchen on the first level in the rear, and we had bedrooms on the second floor. Again, furnished one bedroom. A view that I'll show you is at the top of the stairs, looking out to the top of the stairs, and then the other bedroom view is in the front of the house. So we're looking at the front of the house. We start the fire in the sofa. You'll start to see the flames coming up from the sofa. So the two bottom images there are the first floor. The top two images are the second floor. The middle image on the top is the rear bedroom. So we see the smoke coming up the stair and coming in through the open door of the rear bedroom. Then in the image on the upper right, we see the smoke filling the bedroom that has the open window on the front. That's the only opening to the outside. So smoke follows the path of least resistance. High pressure goes to low pressure. That window serving as a low pressure vent. We start to see flames coming up the stairwell. We see the glow. Then we see flames entering the front bedroom. The velocity and the intensity of the black smoke coming out that window is increasing. And then it's just going to stop. As the oxygen concentration in the house drops below what the fire needs for flaming combustion, the heat release rate comes down, the temperatures come down, and it just condenses the gases to the point where it stops pushing and starts sucking. Once the fire department makes the vent, you can see how that flow path is established with the air inlet low in the door, where we have a bidirectional vent at the front door and a unidirectional vent coming out the exhaust of the bedroom. Fire is going to develop a little bit. It transitioned to flashover within 80 seconds of opening that door. This kind of scenario is basically a trap for firefighters in the past. They would arrive, they see nothing but smoke, they think they're early in the fire event, they might commit resources, people, to go search for victims upstairs, and if the line's not ready to put that fire out, if they don't come in and out of there in less than 60 seconds, they're going to have to jump out windows, jump for their life. Here's a scenario in Washington, D.C., 1999. It's referred to as the Cherry Road Fire. And two firefighters died in this fire. One firefighter was in front of the sofa that you sort of see upstairs, that little yellow block, Firefighter Matthews. And Firefighter Phillips was by the door, which is the vertical rectangle you see on the upper level there. The fire started in the basement. The basement was ventilated. When all the fire department got there, all they saw was smoke. Once the basement was ventilated, it flashed over the basement. High momentum, high velocity, hot gases start coming up the stairs and impacted the two firefighters, and they both died. There was a third firefighter there that received burns over 65% of his body, but he survived to sort of tell us his experience. So these phenomena happen again and again. Funerals are held. But not a lot of change was going on in the fire service in terms of we need to do something different. The leadership of the FDNY, the fire department of the city of New York, said, no, we really need to do something different. They met with their firefighters. They have 11,000 firefighters. They had focus groups. They said, what's it going to take for us to get a better understanding of this? And they said, we need to make sure that the victims are safe. We need to make sure that we're doing the best thing for victims, not just the best thing for our safety. And so that's why these experiments were set up on Governor's Island. We conducted these in conjunction with Underwriters Laboratory. And again, old abandoned federal property that they left in very nice shape for us. It used to be a Coast Guard training base. We had a lot of very similar structures. We could look at the upstairs bedrooms and monitor them for gas concentrations as well as temperatures to look at how victims would be affected. Again, we're using real fuels. The places were left in wonderful condition for us with the wood cabinets, nice carpeting and everything. We just had to add the beautiful furniture. I hope you enjoy the mauves and the purples there. You know, we got a good price on it. We put a lot of furniture in the basement for the basement fires as well, but a lot of the fuel in an unfinished basement is really in the floor assembly itself, the exposed wood at the ceiling. Again, if you look at your furniture at home, you'll see very similar warnings. You know, be careful, don't have this near open flame, et cetera, et cetera. And being as how I'm from NIST and the main point of our business is measurement. I had to include a slide there to give you an idea of some of the instrumentation that we put in these structures. Bidirectional probes measure both the temperature and the pressure so we can get the velocity of the hot gases, whether they're coming out of the door or the cool gases going in the door, or how that changes over time with the fire. Thermocouples, we put hundreds of thermocouples throughout the house so we can see the thermal gradient, the temperatures from the ceiling down to the floor in the various rooms in the house and the hallways and whatnot. We have our gas analysis equipment so we can understand the tenability of victims. Typically, folks in residential fires die due to smoke before they would get burned to death or something like that, so it's important to monitor that. And then again, we run miles of video cable and data, because that's how we're getting this information out to teach people, to show them what's actually going on in the house. So here's a fairly simple case where in the past folks were hesitant to put water in a basement window. They would go inside and try to force their way down the basement. And the reason was that they thought they would push fire, they thought that they would make conditions worse, they might steam somebody inside. But you could tell looking at the thermal imaging view at the top of the stairs, there's not a lot of violent movement of heat. There's no significant increase in temperatures. In fact, the temperatures are going down, and they knock the fire out. So flow water fast as possible on the fire and mitigate the hazard, and things will get better. So water through the basement window, here's how we're trying to share the data instead of in the form of graphs. And graphs, a simple graphic that shows once we introduce water into the window for about 60 seconds, the temperature in the basement in the front went from 1700 F down to 300 F near the ceiling. At the top of the stairs near the ceiling, it went from 600 degrees Fahrenheit to 200 degrees Fahrenheit, and the heat flux dropped from 14 kilowatts per meter squared to 0. Even in the bedrooms remote, the open bedroom remote upstairs, the temperature dropped from 225 to 190. So it made conditions throughout the structure better. And of course, if we had more time, I could show you graphics where we put water in the front door, water in the second story window, move the fire all around the house, and we get very similar results. This is one of the more recent simulations that we've completed in my group at NIST. It's available. There's a nice narrated version. It's about 10, 11 minutes long on YouTube. Just go to the NIST YouTube channel and you can find it on the fire playlist. So it happened June 2nd, 2011. And this incident kind of brings a lot of things together. It brings the equipment, the failures of the equipment, the failures of the radios. This occurred to these firefighters. It appears that their bottles may have heated and they may have ingested hot air from the bottles, possibly. We're still doing some research on that. It talks about flow paths, and it talks about appropriate fire attack. You can see this house is on a nice hillside in San Francisco, 2 stories on the front, several stories on the rear. The fire starts in a lower level on the rear. They call these their upside-down houses. The living room is in the basement. The street level has the bedrooms, and then the upstairs level has the kitchen and dining room. The fire starts near the sectional sofa in the living room. The victims are on the street level. They're there with their hose line to protect the stair. Their hose was there. It was charged. They never seemed to flow it. Between a time that officer talked to them and conditions were fine, they weren't hot, just a little bit smoky, and left. As soon as that officer left the house, he noticed conditions dramatically changed. And the reason they dramatically changed was because the windows failed on the living room level, the lower level, and that level flashed over. The windows were only held in with vinyl frames, no steel supports or wood frame supports. So once they started to fail, the entire wall of windows failed within 2 minutes. So again, our model shows things like how much energy can we get out of this fire. And what you see here from the heat release rate, we had a potential of about 20 megawatts of energy with all the furniture and the carpeting and everything downstairs. However, notice by the red dotted line that due to the oxygen limitation, we're only getting about 6 megawatts out of that fuel package until the windows failed. Once the windows failed, you notice that we shoot up to more than 30 megawatts. Wait a minute. We only started off with potential of 20 megawatts. Where did this other fuel come from? It came from the accumulated fire gases that were held in the structure. Again, that's the hazard the firefighters need to mitigate. So here's a view of the model. As you can see, it's advanced quite a bit since we first modeled Cherry Road years ago. We start to see the smoke from the front of the house. Here we'll get some definitions. So remember, the fire's on the basement floor, and the firefighters that died are on the first floor. As the fire intensifies and the windows fail, they then continue very quickly to fail across the back of the structure. This doorway here on the side of the structure at the fire level is where they ultimately successfully attack the fire. So again, part of the tactics and part of the consideration is, if you size up this house and you determine that the fire would be beneath you, don't put your firefighters in the chimney. Don't put them above the fire. Make your initial attack on the same level as the fire is. And again, we talk about heat transfer rates, and it's a function of not only just the energy, but also of the velocity. So the firefighters are at the bottom of the stairs there at the street level. It's currently blue, which means it's got about 0 velocity, but after the windows fail, we clearly get about 10 miles an hour of movement, and that's even with the flames venting out the rear of that structure. And then we also look at the increase in temperature, which again is another part of the hazard. So before the windows failed, they're 200 degrees F or below, and then after the windows failed, we can see that now they're between 800 degrees and 1200 degrees in the area where they were located. Again, well above what any of their gear can take. We don't only work with large cities and towns. We had a great opportunity to work with the State Fire Marshal's office down in South Carolina and a number of the departments in South Carolina. The burns were actually conducted with the Spartanburg Fire Department. And what we try to show with these burns is different ways, different alternate means of attacking a fire. So in this case, this is somewhat of a traditional means of attack. The firefighter just opened the front door, and in the lower right-hand corner, there's a thermal imaging view where we're looking from the rear of the house down the central hall out through the front door. The kitchen is just off to the left-hand side of that hallway view. In the lower left-hand corner, we just popped open the kitchen door. We allowed about 30 seconds to simulate the firefighters making their way to the kitchen, forcing the door, and then we have a monitor nozzle, a water nozzle in there, that's going to flow 150 gallons per minute of water to simulate an interior attack on that fire. And we flow water for a few seconds, and we start to see it has a pretty good impact. But notice there was a surge of heat that came into the house once that door was open and would have been flowing over the firefighters' heads and causing damage to the interior of their house. Interestingly enough, most of the construction in single-family homes has no fire rating whatsoever. The floors aren't rated, the walls aren't rated, the ceilings aren't rated. The only exception to that in most parts of the country is if you have an attached garage, that wall has to be fire rated and that door has to be fire rated. So in this particular case, using this tactic, the firefighters are going in the structure and basically disabling a fire protection device to fight the fire. Let's look at it from another perspective. Let's look at it to say, what if they hit it from the outside first? So the views you're looking at on the bottom are a video view looking at the inside the kitchen door and a thermal imaging view looking inside the kitchen door. We're not going to open the front door this time. The first move the firefighters make is to take a charged hose line and as soon as possible open it up and flow water in that garage and knock the fire down. So their officer who is doing the size up, that's what the officer's doing, taking that 360-degree lap of the house. He doesn't see any victims hanging out windows or anything, and he's telling his firefighters, let's flow water on that fire. Use the reach of your stream. Notice as soon as the stream gets into the upper layer where most of the hot gases are, the fire goes out immediately. Now they can move in closer, continue to knock down the fire. Notice the condition of the kitchen. Fire door's holding, the kitchen's in very good shape. To be fair, the fire service has reason to be concerned about exterior attack. They say, you know, Dan, we've seen fire being pushed. I've had fire being pushed on me because part of it is you need to use the appropriate tools and the appropriate tactics. So what we have in this building are 2 rooms that are on fire upstairs. If you look at the lower level views, video on the left and IR on the right, we're looking at the small hallway that's about 4 feet that connects those 2 rooms. The hallway has combustible finish inside, which is why it's burning. And in the room that we just attacked with a straight stream, 150 gallons a minute, we're maximizing the amount of water that's getting in the room. We're minimizing the amount of extra air being entrained in the room, and most importantly, we're leaving that vent open so smoke and heat can come out of it, and as a result, you didn't see much change at the top of the hallway. Now we're going to do something bad. Watch the impact. Right? There's your pushing fire. Pushed it down the stairs. We took a fog nozzle and we covered the vent. So now we have a high pressure vent instead of a low pressure vent. High pressure flows to low pressure. We minimized the amount of water that got in there, so the little bit of water that got in there converted to steam. It was very inefficient. And using a fog nozzle like that is the same as putting a fan in front of that window. You're entraining a tremendous amount of air. So you're making the fire bigger, you're pushing it in one direction, and you see the result. Once, even with a fog nozzle, if you step up a couple of steps and get water in the window efficiently, that stops the push and shuts everything down. I'll show you another push. So in this case, we did two different houses with the straight stream on one side of the street, and then I'll show you the fog because obviously the fog's more interesting. The straight stream just puts the fire out. So what we have here are two rooms that are connected inside by a hallway, and the fire room has the bigger window, and unfortunately for us, part of the window pane slid down and is blocking the air coming into the room. So that really slowed the fire down because it doesn't have the oxygen it wants. So we're going to call a firefighter with a pike pole, and he's going to clear that window for us, and then the fire is going to resume its growth rate because now it has the oxygen it needs to increase its heat release rate and increase its hazard. You're going to notice that the smoke pushing out of the target room or the attached room that's not on fire just yet, we're going to start to see flames in the smoke coming out of that little window as soon as it gets lean enough and mixes with enough oxygen as it rolls over the eave. So we'll see a little bit of flame there. It's going to back up, give us a little better view here in a second. There you can see some orange in the smoke there coming out of the small window. And now we're going to do the bad thing and hit it with a fog line. And there's your fireball. So again, the techniques and the tactics are very important. So how do we communicate all this information to the fire service? Well, we try to use our web page as much as we can, nist.gov/fire. And if you're taking notes online, that's the website you want to take, because these other websites that I'm going to show you where you can get great firefighter training information are all listed on that web page. Again, you'll recognize our partners, ISFSI, where we did the Spartanburg burns with them, and they have 3 different programs online. All these programs are available to the public for free because they're funded by assistance to firefighters grants that come from DHS and FEMA. And so that's been a great asset in developing networks to really get this information out to the 30,000 fire departments that are in the United States. ulfirefightersafety.com, they've got 7 or 8 programs online. The basement fires happen to be a ARRR grant that they got from NIST, and we collaborated on that together. So that was a very good opportunity. International Association of Arson Investigators runs CFI, or Certified Fire Investigator Trainer.net. Again, it has information on fire dynamics and some of the other fire fatalities that NIST has studied with their models and experiments. The IFF is the Firefighters Union, International Association of Firefighters. They have several good programs on YouTube that reflect this information. We've been working with NYU Poly, FDNY, and several other fire departments, including Chicago and now LA and Houston, where they're using web-based training options, or starting to. Every firefighter's got a smartphone. And the idea of getting somebody to sit down for an hour at a time or a half hour at a time at a computer terminal is getting harder and harder to do. But if you can push out training to them that they can watch for 5 minutes and come back to it later, or watch in between calls and whatnot, that's a good opportunity. LA County Fire Department, the home of Hollywood, has really taken that mantle and run with it. So they've produced some very high quality videos for training that they're willing to share with other fire departments on their web page. The other interesting thing that they've been doing is they've been pushing out this information for about 10 months, training their entire department online using a learning management system, as well as getting some local resources from the company officers doing hands-on drills. Since they've started that training, they've reduced their firefighter burn injuries by half. So it is having an impact. F-STAR is run through the International Association of Fire Chiefs. Again, it's a portal that's designed for fire chiefs. All the research is sort of boiled down to a one-pager with links that they can give to their training officer or other people to spread through the department. Modern Fire Behavior is another website. That's where all the Governor's Island studies live that were done jointly with UL. The other thing that we see as a success, or that we're making the turn, is that the organizations that develop training materials that they sell to the fire service, that the fire service uses for training for Firefighter 1, Firefighter 2, company officer, et cetera, they're starting to adopt this material into their manuals and sell them. So again, it is reaching the core groups that it needs to reach. And last but not least, NIST used to be called the National Bureau of Standards because a lot of our focus is supposed to be on developing standards for trade, commerce, safety. And we are seeing that the fire dynamics are moving fairly rapidly now into a number of standards that are designed to help firefighters train, and also firefighters' emergency equipment, designed for their emergency equipment. So with that, I don't know if we got any questions online, or we have a few minutes, or...
Yes, we can take questions. Thanks, Dan. That was fascinating and scary, and I want to go home and check my smoke detector.
Absolutely.
I actually have a question for you. We had Dr. Hunter Fanning come and talk about the Net Zero House and how they're working to that. Has your group been working or consulting with their group to try and make sure that what they're doing is not more flammable than previous insulation tactics?
Well, there's a couple of things. Number one, it absolutely is more flammable. But number two, it's a fully sprinklered home. And so they've taken a number of other fire protection precautions intact with building that as well. So again, these things really need to go hand in hand. And you know, I don't want to let the opportunity go for that question about the importance of automatic fire sprinklers. There are 2 states currently that require automatic residential fire sprinklers in every home that's built, and that's California and Maryland currently. Unfortunately, there are other states, and automatic fire sprinklers are in the model codes for residential homes. And unfortunately, there are other states that are actually passing laws and mandating that the localities cannot implement the model code to give their state occupants that level of fire safety. And you know, it's kind of crazy as we see these incidents across the United States. And fire's one of those things, and where most people think that that's not going to happen to me. The number of fires are going down. We don't see fires. We're more likely to get into a car accident, certainly. But the problem is, as we had a tour of the library earlier, and there was some concern about the fact that there were sprinklers in the library and what damage that might do to the books. You know, I pointed out to the head librarian, you know, you can dry stuff off, but you can't unburn it. And so sprinklers are a very important feature, but at a minimum, you want to have smoke alarms. Smoke alarms are inexpensive. Don't limit yourself. Put one in every sleeping area. Have one on every floor. Again, the tragedy that happened earlier this week in New York, you know, perhaps, but for a couple of smoke alarms, it might have been a different outcome.
Anyone else online or in the room with anything to ask? Here. Okay. Here.
2 questions. The first is hopefully brief, and that's, what impact does a metal roof have on a residence and fire behavior?
Well, a metal roof, as you might imagine, doesn't contribute to the fuel load, so that's a pretty positive thing. It's not made out of tar or other material there. It's not made out of wood shakes, for example, so that's a good thing. It's going to seal fairly well. Any heat that's under it, it's going to radiate back into the space. And so interestingly enough, there was just a research program conducted by UL on attic fires. And again, you want to coordinate your ventilation. You don't want to open things up too much before you're ready, because the attic, as long as it maintains its shape and its compartmentation, is going to limit the amount of air that gets involved. and limit the amount of fire spread. So if you can get water into that space and start to cool it off early before you start to vent to let the smoke and the toxic gases out, you'll be better off. So, the metal roof doesn't have any, typically the firefighter saws can cut through that pretty easily and that sort of thing. The advantage it would have from a fire perspective is it doesn't add any additional fuel.
Okay, and the follow-up question, I'm sure many of us are thinking the same thing. What do you do if there's a fire in your house? What are the steps, given all the new research, that people should take?
You need to get you and your family out as soon as possible. Don't, keep your smoke alarms in good shape. When you hear the alarm, get out of the house, stay out of the house. And in fact, as you're leaving the house, you can do yourself a favor from a property perspective and the firefighters a favor by closing the door and slowing down the fire growth rate until they get there. You want to practice an exit strategy so that your family knows where to meet in case they have to come out different doors or different windows. And there's a lot of information, free information online from USFA on how to practice exit drills and fire safety information like that.
Okay, just to be a little bit more specific, what if the downstairs is on fire and it's not safe to go downstairs? What should you do with the upstairs bedroom?
You want to isolate yourself. If your bedroom door wasn't closed to start with and you see that you can't get downstairs to get out, close the bedroom door. If you open the bedroom window, keep in mind that you may actually draw more smoke in. So if you're going to open the window and get out, you need to do that. Get on the phone, let people know where you are, and get help there as soon as possible. The door will protect you for a limited amount of time, minutes, but you may need to look at getting out that window.
Do you happen to know how structure fires or wildland fires affect radio wave propagation, the communications devices that firefighters use?
Not so much. We're working with some folks out at Boulder, Bill Young and some other people, and they're working with us where we're testing the radios in terms of heat. They're looking at how that impacts the signal and the signal strength. We know that sound is impacted by heavy amounts of soot and smoke with regard to like the pass device, the warning alarm that the firefighters have. So if they go down and they're motionless, this pass device would start to give off a 95 decibel sound so that their rescuers could help zero in on them and find them. And there's been some research at the University of Texas, Austin, and some other places recently that indicate that, that does have a pretty big impact on the sound waves. We don't know about the radio waves. But, soot has a lot, it's particulate matter, and so potentially could provide some level of interference.
Great. We've one more from the people on WebEx. What are some of the ways the average firefighter is using technology to improve operations?
A lot of fire departments are the new technology, if you will, might be thermal imaging cameras. And the important thing with any technology is not to just make the deal with the mayor and the councilman and whatnot and get that technology in your firefighters' hands or your fire officers' hands. You really need to train them on how to use that technology. If they don't understand what the capabilities as well as the limitations of that technology are, you may not gain any improvement in performance or any improvement in safety. But thermal imagers are being widely used. There is a lot of training going on, and they're extremely valuable for sizing up a house to locate where the fire is. You really want to locate where the fire is before you make entry. And then you can make some decisions then, instead of going in the smoke and searching for the fire, try to make some decisions of where you want to attack the fire. And it may be from the inside. That may be the fastest way to get water on the fire. In other cases, it may be taking a line around to the rear.
And unless there are any other questions, I think that sums it up. Dan, thank you so much.
Thank you. I appreciate the
Informative
opportunity.
and great. And for those asking online, the video will probably be available in a few days. We will post it to library.doc.gov. You can click on the View Past Events link on our calendar on the left. Thanks, everyone.
Great hosts. Thank you.